Looking at a system of three linear equations can feel overwhelming. The variables are scattered, and it is difficult to see the underlying structure of the problem. We can snap this chaos into an organized, readable grid using the matrix equation AX equals B. This bracket format pulls the coefficients, variables, and outputs into their own distinct blocks. Matrices are more than just boxes for numbers. They are a specialized toolkit for organizing complex systems and calculating how objects move and transform in space. Define your grid by counting rows, then columns. This is a 2x2 matrix. To add matrices of the same size, combine corresponding elements for the new sum. For scalar multiplication, a single number outside scales every element inside by that factor. Mastering these simple element-by-element moves is the first step. Once you understand the basic arithmetic, you can begin to look at how different matrices interact with each other. Matrix multiplication follows a strict dimension rule. You cannot just multiply the corners. Instead, the number of columns in the first matrix must equal the number of rows in the second. If those inner numbers match, the math can proceed. The outer numbers dictate the size of your result. A 2 on the far left and a 3 on the far right mean you're building a brand new 2x3 grid. To fill the first slot, take the first row of the left matrix. It lifts up and rotates 90 degrees to slide down the first column of the right matrix. You multiply the paired numbers and add them together to get your value. This row-by-column process is how we mathematically represent the combination of two different spatial transformations into one. To manipulate the entire matrix at once, we use operations like the transpose. This simply flips the matrix over its diagonal, turning every row into a column. To find the determinant of a 2x2, multiply the main diagonal and subtract the product of the opposite diagonal. This result measures how the matrix changes area. If the result is 0, it means the transformation has squashed the two-dimensional plane into a flat line. That determinant is the key to finding an inverse matrix. You multiply the grid by 1 over the determinant. If the determinant is 0, you cannot find an inverse because you cannot divide by 0. When an inverse does exist, it allows you to reverse a transformation. It acts like matrix division, letting you isolate your variables and solve the system. For larger systems, we use row reduction on an augmented matrix. This allows you to solve the system using only 3 moves: swapping rows, scaling a row, or replacing a row with the sum of itself and another. You start by selecting a pivot in the first column. Use your row operations to force a 0 into every position below that pivot. Then move diagonally down to the next row to find your next pivot. Let's try it. Look at the 5 sitting directly under our current pivot. Pause the video and write down the row replacement formula you need to turn that 5 into a 0. The correct move is to take row 2 and subtract 5 times row 1. Mastering this specific replacement move leads you to reduced row echelon form, which reveals the final solution for every variable. After row reduction, you count the number of pivots to find the rank. If every variable has its own pivot, the system is fully defined with one unique solution. But if there are more variables than pivots, those extra variables can take any value, resulting in infinite solutions. You can also see this geometrically. A matrix acts as a transformation, skewing the grid and knocking vectors off their original paths. The amount a vector scales by is its eigenvalue. These identify specific directions, staying aligned even while the space is warped. This toolkit is the foundation of linear algebra. Screenshot this summary of the dimension rules, the determinant formula, and your 3 legal row operations for your next study session. Remember to double-check your signs and your pivot positions. Matrix fluency comes through repetition, so keep practicing the steps.